Hey everybody, I'm Chili. Welcome back to Beginner C++ Tutorial 24. This is going to be the final video of Beginner C++. This is it, people. The end. But don't worry, I'll be back with Intermediate C++ in no time at all. In the meanwhile, let's take a look at today's topic, which is recursion. Now, you might be asking, what the fuck is recursion? I've heard about this shit. What is it, Chili? Well, I'm not going to tell you, not yet. Now, we got to set up the motivating example, because that's how I roll, that's how I do things. So, let's look at Minesweeper here. You got your mines, you click your tiles, you find a tile that is empty, that's blank. That means that there are no neighboring memes, so you're free to just click these fuckers. And then these ones also have no neighbors, so you're free to click those fuckers. And you just keep doing this mindlessly until you run out of blank tiles like this, which could take a while. And you know what? Cue future Chili, cue the video. You know the one.
I said, "Oh Lord Jesus, it's a fire."
So there must be an easier way, and let's look at Minesweeper, the one that's on Windows 7. You click a tile and that's blank. This is what happens. Automatic. We're living in the future here. We want this. So how do we get this? Well, you might think, okay, well, I got an idea, Chili. Just don't save. I got an idea. So in meme field, right? Memefield.cpp. So when we count neighbor memes, we're just looping through 9 tiles that surround a particular tile, the tile that is at grid pause. So if we reveal a tile like this and we find out, oh shit, that shit is blank, we're safe to go like this. Oh wait. Color's kind of weird. Safe to go like this. There, blam, 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 blam. Right? We can reveal all these guys because we know we can do it. So all we got to do is loop from this tile here, 1 to the top left, down to 1 to the bottom right, looping across like this. Loop through 9 tiles, reveal all your shit. And that will get the job done, won't it? Well, sure. First off, we're going to need a function. We're going to need a function to test if a tile, has no neighbors. So let's do that. We'll go bool has no neighbor memes const. There we go. And then we're going to implement that fucker. So what is that going to be? It's going to be n neighbor memes equals 0, and if that is true, then it has no neighbor memes. So there we go. Now we've got our function that we can test for shit. Now what we're going to do is we're going to go into what? We're going to go into on reveal click, and first thing we check is, does it have a meme? You're fucked. Did you win the game? You are WinRAR. Otherwise, one more check. Else if tile dot has no neighbor memes. If it has no neighbor memes, we just want to reveal all the surrounding tiles, right? So we can go down here, and we could probably just copy this. There's a beautiful thing, and the beautiful thing is I named this grid pause, and I also named this one here grid pause. So if I just paste this code in here, it just works. It just fucking works. Well, mostly, we'll see. Now what we want to do is we don't want to count the tiles. We want to reveal those fuckers. So we go, if tile at grid pause, this is the new grid pause, this is the grid pause of the loop, not this grid pause. I know it's confusing, but remember, scope, this one covers up this one because it's in a, it's a closer scope. So if tile dot grid pause has meme, then no, we don't want to do that. All we want to do is, actually, what we're going to do is we're going to go tile reference tile is equal to tile at grid pause. And then we're going to check to see, we want to check to make sure that it's not revealed already. So if not, tile dot is revealed, because if you try to reveal a tile that's already revealed, you're going to trigger the assertion of death. So we want to go tile dot reveal. So here we're going to reveal all the tiles in that 9x9 or the 3x3 square that aren't already revealed. And if we do this, build solution, and if we run it, and if we click this guy, sweet. Now we get some revealing action here. It's pretty good, but it's not the greatest. It's not, we can do better, right? Because think about it. We still got to do a bunch of bullshit clicking to get it. It's faster, but it's not best. It's not Chili good. You know what I'm saying? It's not up to Chili's standards. So you might say, well, Chili, I got you here. I got you. All I'm going to do then is when I reveal the tile, I'm going to put like another check in here. Listen, Chili, I got this. Check this out. I'm going to put another check in here. I'm going to put another check like this. I'm going to put another one. And so we're going to reveal the tile. And then if tile has no neighbor memes, we're going to go through another loop. We're going to do it again. Chili, this is going to be so fucking good. Watch me now. Bam, look at how much I revealed this time. You don't even know how revealing my tiles are, but that's retarded. If you got like a really big field, how many of these fucking loops are you gonna have to put? I'm gonna put some loops in my loops. In my loop, this is programming. If your code looks like this, you're probably doing it wrong, bruh. So there's gotta be a better way to do this, is what I'm trying to say. And spoilers, it might have something to do with recursion. So what is recursion? Now, recursion is the phenomenon or the technique of a function calling itself. And that might sound dumb if you think about it, because if a function calls itself, that function's action is to call itself. So it calls itself again, which then it calls itself, and then it calls itself, and it's just like, it's infinite. It's what we call infinite recursion. It's no good. There's no end. You're going to be doing that shit forever. Only it's not actually forever, because when you call a function, it uses a little bit of memory in a place called the stack. Every time you call a function, it uses up a little more stack memory, and every time you return from a function, that memory is freed. But if you keep calling and calling and calling and calling and you never return, you're going to run out of stack, and you get a stack, what's called a stack overflow. Let's try that. So I create a member function in game. I call it we are fucked now, and let's create a definition for we are fucked now. And recursion, so we call ourselves. So let's call we are fucked now. And let's put a breakpoint here for fun. Oh wait, we have to call the function from somewhere though. We got to start the recursion. So let's call it from game, from our constructor. We call we are fucked now. And I'll put a breakpoint there. Actually, let's not put a breakpoint here. Let's put a breakpoint here inside of we are fucked now. So we run, constructor calls this function, here's our call stack. Game constructor calls we are fucked now. If I continue, we are fucked now calls we are fucked now, calls we are fucked now, calls, and it keeps going and keeps going. And if you remove this breakpoint and you just let it run, you get stack overflow. Basically, it just called itself a lot of times. If I break here, we can see how many times it called itself. I don't know how many that is, but it's a fuck ton of a lot. And we ran out of memory on our stack, and program puked. So probably a function calling itself infinitely is a bad idea. We can agree on this. So what we need is what's called a terminal condition, and that is a condition that will cause the function to stop calling itself and instead return. So what we can do is let's just pass in an int here, pass in int n, and we're going to create a recursive function. It's not going to do anything useful, but it will have the nice effect of not fucking us. So we're going to go int n, and we're going to put a little conditional in here, and if n is equal to 0, return, else call we are fucked now n -1. Now, what do you think this is going to do? First of all, we got an error here because now we take a parameter. So let's put in 5. So what do you think is going to be, what's going to happen when we call this function? What procedure is the CPU going to run through? Get it in your mind. Pause the video if you have to. So I'm going to put a breakpoint right here, and I'm going to run. So first thing that happens is we enter we are fucked now. We call it with a value of 5, so n is equal to 5. Is n equal to 0? No. So let's call we are fucked now again. We call it with n minus 1. So this time n is now 4. And we can go again if we run. It's going to call we are fucked now with n minus 1, which is going to be 3, 2, 1. Now we've got our call stack building up here. Run it again. 0. So now we've got 1, 2, 3, 4, 5, 6 calls in our call stack. What is going to happen now? Well, n is now 0. So instead of calling ourselves once again, we are instead going to break the cycle, break the chains, and we're going to return. So we're going to go into here. And when we return, I was kind of hoping it would show them returning one by one from those functions, but I guess I should have clicked this one instead of this one or something. It doesn't matter. Who cares? The idea is that now once we reach n is equal to 0, that call, the very top call of the stack returned, and then the next one returned, and the next one returned, and the next one returned, and we're back to where we started, and our program doesn't crash, and we can play Minesweeper now. Yay! Alright, that was a pointless example that does nothing useful. Now let me give you another pointless example that does something useful. So, factorial. You might not know, but a factorial is written like this. Let's say it's like 5 with an exclamation mark in front of it. Or maybe it's behind. I can't remember if it's in front or behind. Anyways, so it's written 5 with an exclamation mark. And what that means is 5 times 4 times 3 times 2 times 1. Which is 20, 60, 120. I'm going to say that's equal to 120. So 5 factorial is equal to 120. Or, for example, 4 factorial would be equal to 4 times 3 times 2 times 1 is equal to 12 times 2 is 24. Okay? That's the basic idea of factorial. So we can write it like this, but you could also write factorial in recursive form. And what does that mean? Well, for example, you could write 5 factorial is equal to 5 times 4 factorial, because 4 factorial is 4 times 3 times 2 times 1, and 5 factorial is 5 times 4 times 3 times 2 times 1. So 5 factorial is just 5 times 4 factorial. Likewise, 4 factorial is equal to 4 times 3 factorial. So we could rewrite this in general form as n factorial is equal to n times n minus 1 factorial. So, the factorial of something is equal to n times the factorial of n minus 1. What does this look like? Well, go back to our fucking function bullshit here. We call a function int n. We call ourselves again n minus 1. What is this doing? Doing a factorial is doing factorial of n minus 1. It looks the same, right? Maybe we can use this technique to solve our factorialization. Now, the only thing is we need a terminal condition. We can't just keep going n minus 1. And the terminal is, we know that the factorial of n equals 1 is going to be 1. So we'll just return 1 for that. So let's do this again. So I'm just going to call it we are fucked. But we got our return of value now. It's going to be int. And let's go back into this fucker. So we are fucked now. This is factorial. It's a little known synonym for factorial. We are fucked. So if n is equal to 1, just return 1. Otherwise, return n times factorial of n minus 1. So this is the recursive solution to the factorial problem. So if let's just go int factorial 5 is equal to, we are fucked now of 5. So this should give us, I forget what it was, maybe 120? Yeah, sure. So fact 5 is equal to garbage number, and when we step over, equal to motherfucking 120 bitches. So we can use that to calculate, we can use recursion to calculate the factorial. Now, should we? The answer is, of course, no, because it's obvious that this operation here could have been calculated with a simple loop, and it would have been easier to understand with a loop. So you might be saying, well, if we could have used a loop for this, then what's the point of recursion anyways? Recursion is dumb. But here's the thing. Loops work great for when there's only a string of calls. One function calls itself once. But when you have a branching structure like this, when one function maybe calls itself 1, 2, 3 times, and then that one calls itself 1, 2, 3 times, and that one calls itself 1, 2, 3. This kind of tree branching structure, instead of just a line of calls, when you get to this tree, you can't do that easily with a loop, and that's where recursion really shines. Now let's look back at our revealing problem. We reveal one square here, and if that one is blank, then that means we want to reveal all 8 squares around it. So we want to now call reveal recursively on these guys. And if these guys are blank, we want to call reveal recursively on all the guys around them. And if they are blank, and so on and so forth. So this isn't just a single string of recursive calls. This is a tree. It's a branching tree branching out in all directions, and therefore this shit cannot be done very nicely with loops. It's not impossible, but it's a fucking pain in the ass. With recursion, it becomes elegant, beautiful. You want to make sweet love to it. So let's get on that shit. Let me undo my changes to game.h and game.cpp. We'll return that back to the way it was. Hopefully I didn't lose any actual useful changes. Otherwise I'll be fucking pissed off. I do that shit all the goddamn time. So, what do I want to do? Well, I want to make a recursive function here that is going to do my bidding. So we're going to go private. And we're going to go void reveal tile. And we're going to go constant v2 ampersand grid pause, because that's how we roll. And not const, because we're going to be changing shit. We're going to be revealing shit. That's what we're going to be doing. So reveal tile is going to be calling itself at some point. We know this. It's also going to be there's going to be a terminal condition. So what are we going to do? Well, first thing we do is if we want to reveal the tag tile. If we're going to reveal a tile, we got to follow the rules of revealing tiles. So it's going to be this stuff here, right? But let me think here. Say is meaning grid position. So the question is, how much do I want? What is the division of labor between on reveal click and reveal tile? Who is going to be doing what? Who is going to be doing the conversion from screen to grid? Who's going to be doing the assertion test? Who is going to be making bacon on the beach is what I want to know. Reveal tile. I'm going to say this is what reveal tile is going to be doing. So it's going to get the tile at the position. It's going to check. It's going to be responsible for checking to see if it's already revealed or flagged, and then do the shit. You could have divided it up in other ways. It doesn't really matter. But let me think. Yeah, this is actually, this makes sense. Okay. Maybe it does matter, maybe it doesn't, I don't know. But anyways, this is how I will recommend you to split it up. So you get a grid position, and you call, first of all, you get a reference to that tile. You're going to be using that reference to do a bunch of checks and bullshit. So you reveal the tile. If it has a meme, you get fucked, mate. 1. Otherwise, and here is where the magic is. So if this is false, you're just going to return. That's the terminal. But if it's true, you are going to recurse. And that means you're going to call yourself in all directions. So what we're going to do is we're going to make use of this bullshit here. Smoke them if you got them, gentlemen. And we are going to call reveal tile on all of the 9. Fuck. That was a fail of copy and pasting. We're going to call reveal tile in all the directions. So on all 9 tiles in that grid. So grid pause reveal tile. And what that is going to do is, it's going to call reveal tile on all. It's going to call it on the same tile again, but I don't care, because when it calls it on the same tile, it's already going to be revealed, and so it's going to fail this, and it's just going to return right away. So it's fine. It's fine. We don't need this count here. Get out of there. 1. Yeah. All right. So reveal tile. This is the recursion part of the program today. And this should maybe work, maybe it won't work. I don't know. Who cares? Let's go into on reveal click, and we're gonna call reveal tile grid pause. So this one will start the recursion. Gentlemen, start your recursion, and then it'll just keep going. And if game is 1. Yeah, so we'll also keep calling game is 1 every time we recurse, which could be a little expensive. Maybe we don't want to do that. I mean, it's just an optimization thing. It's not a big deal. The game will run the same, but I am a bit of an optimization whore. So if tile has meme, I mean, honestly, this could be done in here. This test isn't really necessary for the recursion part, but it's necessary for the initial reveal, because it's possible for the user to try to click on a bomb, right? After that, the recursion will be safe, because you never try to recurse unless you have no neighbors. So, we'll leave this in. This is simple. It's a quick test. This will cause a lot of unnecessary processing. So we'll cut that out. And we'll put that after we reveal the tile. So we reveal the tile. Then we do one test to see if we've won the game yet, as opposed to one test every time we recursively open tiles. And that will make our CPU a little less, I don't know. I don't care about the CPU. CPU is my bitch. That's what I always say. But anyway, so this might work. Let's try. Open. Nope. Open. Fuck. No. Doesn't seem to be working though. All right, so a quick inspection has revealed to me once again the dangers of copy and pasting, which is here I've got this test here to test if it has meme, because this code was originally from the meme counter, but of course we're not counting memes, and it's impossible for the tile to have memes because of the test that we had before checks if there are no neighbor memes. Then how can it have a meme on one of the neighbors? That's impossible. So get rid of that, get rid of that, get rid of that. Build this bitch. And now, show me the recursion. Oh, did you see that? It's so good when it works, though. It's so good when it works, though. And then we do that. And no. That's good. And this is going to have one tile. This is going to have one. This is going to not have one, not have one, not have one. I win. Congratulations, I win. Where is me? All right. So, I mean, that's recursion. And it's pretty fucking sweet. And I like it. And I also introduced you a little bit. I showed you a little bit of the stack. And that's a sneak peek, because in the beginning of intermediate, I'm going to be talking more about the stack and about some low-level memory bullshits. And it's going to be interesting. It's going to be good, but that's a story for another day. Now, for those of you who are thinking, Chili, this recursion shit, it's great and all, but I don't really get the big deal. You know, I'm not that into Minesweeper. What's the big deal about this recursion stuff? Well, one thing I'd like you to know is that recursion is used in a bunch of different shit, in search algorithms and in artificial intelligence, like the algorithms that are behind chess programs and Go programs. They're all at their core, they're based on recursion. So, you know, if you're into that shit, then you gotta learn recursion. So there's something for you to think about. I hope you enjoyed the video. There isn't gonna be any homework for this one. I'm just gonna let it roll. I got a new tutorial series to draft up. I ain't got time for this. So if you want homework, you make your own goddamn homework. But anyways, if you enjoyed this video, please click the like button. It helps me out a lot, and I will see you soon with some more intermediate C++.